Hardware to Save a Planet explores the technical innovations that are giving us hope in the fight against climate change. Each episode focuses on a specific climate challenge and explores an emerging physical technology solution with the person bringing it into reality. I'm your host, Dylan Garrett. Hello and welcome to Hardware to Save a Planet. We get to talk about batteries today with Moshiel Biton, CEO and co-founder of Addionics. I've been really interested in doing an episode on batteries because they are, of course, key to electrifying a lot of things like cars and trucks, and electrification is critical to decarbonizing our economy. Just taking transportation alone, it's responsible for something like 20% of emissions globally. So that's a big place batteries can help. Of course, we already have batteries for some cars and trucks today, but improving their performance, safety, and cost will increase adoption and potentially make them more suitable for more applications that today's batteries don't serve very well. Moshiel's company, Addionics, is making a game-changing improvement to batteries. They're one of only 12 winners of the prestigious Bloomberg NEF award for this year. And their solution is a great fit for Hardware to Save a Planet because they're one of the few companies I know of that are focused on changing the physics of batteries as opposed to the chemistry. To introduce Moshiel quickly, he's truly a deep technical expert in the field. He did his Ph.D. in material science at Imperial College London with a focus on batteries, and he co-founded Addionics in 2017 with two of his professors from there. I think what he has accomplished is a great example of finding commercial impact from academic research, which is no small feat. And I'm really excited to learn more about it. So welcome, Moshiel. Thank you for joining us.
Thank you, Dylan. Really happy being here and very excited to participate in your podcast.
All right. So let's start with your background and how you ended up on this path running a company addressing a major climate challenge. Were you motivated to fight climate change early on, or did something else lead you here?
No, so it started, I think, at high school when I really liked to focus on physics, engineering. Then at university, it was natural for me to study engineering. I did like a bachelor degree and master's degree in Ben Gurion University in Israel, in Sheva. And the master's was focused on semiconductor to better understand like performance of semiconductors, how it's going to implement in applications. So it was more applicable research, applied research, than just theoretical one. Lots of experiments in labs, lots of nanotechnology. And my professor back then, supervisor, which was the head of the nanotechnology center at the university, tried to convince me to stay and to continue for a Ph.D. And I didn't want to disappoint him. And I didn't want to do a Ph.D. I wanted to go to work in the industry and to make an impact, but not through the academia. And the result was a bit shy to say that I don't want to continue. So I said, if to continue, I will do it only abroad because it would be very boring to study in the same university and to do all the degrees there. So fast forward, I found myself at Imperial College in London doing a PhD in the field of batteries. And it was completely different from semiconductor. So everything was new. I learned everything from zero, from scratch. And after like few years in the field, I started to understand the value. Back then in 2012, it wasn't sexy or in the news as it today. The days of, in Israel, especially in Israel, days of a better place, the collapse of this company, if you familiar with the dream of swappable batteries for electric vehicles, $1 billion company that disappeared like as it started, which was a big vision, but unfortunately, we see only today companies like doing maybe like 10, 12 years later, it's becoming more realistic to do those type of things. And it was some change and even a big bet to move from very stable industry semiconductor to battery, which wasn't very advanced or attractive as the semiconductor. And in the early days in the battery domain, I felt the difference. I felt like And I asked myself, why we don't see more talent, more young people in that field. And I think thanks to Tesla, thanks to Elon Musk, we saw like a big shift, and batteries became not only essential a tool component, but become also very attractive to young people, young generations and kids to better to understand, to try to understand battery, to learn to study battery. And you asked me about like how if I had a passion from the beginning of fighting climate or being in that field. So always I wanted to be part of the energy. Also in the semiconductors, we developed sensor for solar panels and for energy devices. So it was connected, and I really wanted to be part of that. But to start a company, it was just inspiration that was stronger than us. Like three of us, we found the idea of making Addionics to establish the company. And it's not like just we said, okay, we must open a company and this is what we're going to do. It was the opposite. So many entrepreneurs telling you that you're, I don't know, in one room, they had ideation to try to think what they're going to do. We knew what we're going to do from day one. So it was very clear. I got the inspiration of the company, as you mentioned, like during my research, we research a phenomena which you want to prevent in batteries, you want to avoid, and what we understand and together that we can take this byproduct and turn it into benefit. And that's how the company started. And fast forward, as you mentioned, we're already like 5 years active and in super exciting like timing in the industry of the energy field. And we appreciate every day going to the company, to the office and see the changes and the progress. Very, very exciting.
Yeah, it's cool. A lot has changed in that time frame in the battery space. I think you mentioned around 2012, which is when you kind of got into batteries, which was, I think that was the year, I was just looking at this, the year that the Model S was launched, right? So Tesla was just kind of becoming this mainstream thing. And like you said, they've been a big part of why batteries are such a big deal on everybody's minds today. Batteries are something we all use every day. And I know myself, I know embarrassingly little about how they work. Would it be helpful if you could just describe kind of how a typical battery works?
Sure. So battery, it's a closed energy system. It's different from like an engine or combustion engine vehicle that you have a system which you always inject fuel. In a battery, it's closed, so the fuel that you have in the battery, it's the maximum amount of energy that you can use. And in every battery, you have like three main components. You have two electrodes, an anode and cathode. You have electrolyte and you have separate. You have negative electrode and positive electrode. And the batteries, and especially lithium-ion batteries, called lithium-ion batteries because the lithium ions are moving from one electrode to another electrode. And during that move, they are either releasing electron or getting or receiving electron. Because there is a chemical reaction when this electron is released or received. When it's released, it's the discharge. When you are operating your device, you can collect the electron and operate your laptop. And when you charge the battery, you are receiving electron and store this electron so you can use it at later stage. And it's reversible reaction. So that's the reason that you can charge and discharge. And the anode and cathode, they are made from different components. Most of the anodes today are made of graphite. There are also companies and lots of efforts to replace the graphite with silicon, which is more energetic. And on the cathode side, you have metal composites that store the energy on the cathode side. And always you need to match between anode and cathode because you want to balance to have the similar amount of ions that can travel from one side to another side. Why there is a separator? The separator role is to make sure that only ions can transfer from one side to another side, but prevent contact, physical contact. Because if we're going to have a physical contact between something which is negative, electrode negative to positive electrode, we are going to get a short, and in extreme cases, even like fire and explosion. We want to prevent like physical contact. And the electrolyte is what actually transfer the ions from one side to another side. So that's how basic battery, I would say, work. It, of course, depends on different chemistries and different systems, but that's the basic structure and definition.
Okay, that's super helpful. So the general construction of a battery is two electrodes, a cathode and anode, with an electrolyte and a separator in between them. So tell me, now that we have that context, where in the battery your innovation is being applied.
So the innovation is on the electrode level. Each electrode consists of two components. So you have the active material on the anode, as we mentioned, like graphite, for instance, and you have the current collector. The current collector, it's a 2D metal foil, similar to the foil that you have in your kitchen, and it's a dense 2D. On top of this foil, you spread the active material, the chemistry, and together, after like few processes, you get an electrode. That's the electrode that you can use. And what we do, we are changing the structure of this electrode. Instead of having 2D metal, just 100%, I would say, dense. What we do, we are making 3D metal structure, scaffold. So we are creating more real estate. We can increase the surface of the metal. We can load more active material and increase the surface area. It's in the same space. We can load more material, and simultaneously we can improve the contact between the active material to the metal. So think about, I would say, a sponge or a scaffold or a web where we can add more material. By doing that, we can kill a few birds in one stone. One of the main challenges in batteries is the trade-off between energy to power. It's similar to this glass of water. If I will have more water in the glass, it will take me more time to drink. Similar to batteries. If you want more energy, we're talking about electric vehicles, so longer range, it means that we need a bigger battery. But it will take us more time to charge a bigger battery.
And just quickly, energy is kind of the total amount of energy in your glass analogy, the amount of water in the glass.
Exactly.
And power is the rate at which that energy can be discharged.
Yeah, it can be consumed. Yeah, the speed, the acceleration, how fast you can drink the water. And it depends like about the size of the battery, of the glass. So what we're doing, we're changing the structure in a way that this dynamic is changing. So the trade-off is minimized dramatically between the power and the energy. Today, to solve this issue, there is a need to change the thickness of the electrode. A very thin electrode will give you high power. You have very short distance between the active material to the metal. So you can drink faster, or you can extract the energy much faster. And if you build a thick electrode, you have more energy. But there is a trade-off. With thin electrodes, they are very good to power application, but very bad to energy. And if you want to have like enough capacity, you need to have many, many layers. So this is also going to be very expensive, 50% more expensive than a thick electrode. And thick electrode will provide you high energy, but you are going to have lots of limitations in power, diffusion limitation, poor mechanical stability, so very poor lifetime, because if you have very thick electrode, more tendency for separation, elimination, cracks, similar to a cake. If you're going to have very thick cake, probably it's going to collapse. And that's something that we're changing. We're changing the mechanical structure by having inside the cake like sticks and scaffold that can hold the active material together. And in terms of shortening the distance of the path of the fusion, we have very high contact area. So the effect, we can build thick electrode with a distance between the metal to the active material, which is very similar for a thin electrode. So we can reduce the resistance dramatically by 50% and more in the battery. So get very good effect for power, but simultaneously we can have also high energy. And also it's resulting in cost, because if we can have like thicker electrode, by definition, we're reducing the cost using less layers, less inactive material, more active material, more energy density. So it's associated with cost reduction. And where we're talking about cost reduction, our goal is to have at least 10% reduction in cost per kilowatt hour. So this is something which is very important for the industry if we can reduce the cost. And we talked about stability, mechanical stability. It's associated with lifetime. So it's another advantage. And also thermal stability or conductivity. So it's similar to the, I would say, thermal and electronic conductivity. It's going to be much higher thanks to the nature of the structure. If you have just a 2D layer and you have very good conductive material, and on top of that, very bad conductive material, the dissipation is not going to be through the non-conductive material, only through the conductive element. And we are creating a 3D scaffold, so the dissipation is happening along all the directions. So that's another advantage which is associated with safety and lifetime.
Maybe, and back to your research and where this came from and about how batteries explode, I guess I can start to see the connection. You were understanding why batteries were exploding and how making this 3D structure would improve safety and mechanical reliability. Is that the connection?
Yeah, we can relate it to that, with the background, but of course, the idea, the concept was there from day one, but how we've managed to develop that, it's of course changed along the way, and we always wanted to make it, as mentioned, like cost effective. So in order to make it cost effective, we needed to compromise on some features or some, like, I would say, more ideas that will be helpful for the performance. Bottom line, we want to make it cost effective. At the beginning, we wanted to be able to customize it for any geometry that is going to provide improvement. And we realized along the way that we need to be very cost effective and only think about geometries that, with the limitations that we have, being cost effective, being chemistry agnostic. So whatever chemistry is going to be in the market can benefit from those structures, being able to integrate it to existing production line. So only those structures that have been able to tick all those criteria, been able to move into the later stage of production.
Maybe a silly question, but what does it look like? These kind of microscopic structures, or would just look like a film if I held it in my hand? Or
yeah, we are the starting point. We are taking the thickness of foils today in the industry, and there is a trend to reduce the thickness dramatically on the anode side, even like 6 micron, 8 micron. So we can build foils or metals in that thickness, but to make them porous with a real structure, with a real V direction. So we have a porous structure and a shape that can provide the ability to load more material and also to have better stability and better conductivity.
And so you mentioned cost reduction, safety. What about some of the other key characteristics of batteries like energy density, capacity, charging time? How are those things impacted?
So as we are building high value components, it's not like a standalone battery. Our vision is to implement this technology in every battery in the world. We are always dependent on the type of the chemistry. So it's a question like where we're going to apply it, for what chemistries, for what technology. So if we take like a reference and compare technology, we're talking about like percentage of improvement compared to the reference. So it's not like definite numbers. And with some chemistries, we have much higher improvement because by definition, they already have very poor performance. So you can get higher improvement. But with some other chemistries, which already you push the limit with the performance, the improvement is lower. but still we see improvement. And so it really depends. We've been demonstrated, as I mentioned, like reduction of internalization by 50%. So we can also charge faster those rates. And in terms of capacity, theoretically, we're talking about like by changing and optimize the structure, we can load more material by 20% theoretically. But in reality, in practice, we can increase it and make it much faster because this is also associated with the ability to access this capacity. So if we can make it 20%, but in real time, we can access all the 100%, which is different from the real world. And I'll give you just an example to make it simple. You buy today electric vehicle, a vehicle that can run for 300 miles. This is in theory. In practice, you drive in different roads, different conditions, aircon, not aircon, highway, you have traffic jam. All of that is going to affect your true range. And the reason it's mainly at high speed, by resistance, so the capacity is there, but you have a block, you cannot access that capacity. So what we do with the fact that we can reduce resistance by 50%, we're removing that block. So if it's 300 miles, and in reality it's 200 miles, what we can do, we can take the 300 miles, increase it by 20, 30%, let's say 400, and access all the 400. So at high speed rate, and I would say charging rates, we can really, or discharge rate, access higher capacity.
Like double the capacity in that example.
In reality, yeah.
Yeah. That's a pretty big deal, right?
Yeah, of course, it's in extreme use cases. If you are going to drive very slow in the city, it's not going to double it. But the ability to load more material and to access more material simultaneously, that's something was unheard of in batteries. And that's what we are changing. Only by physical structure. And that's the message. That's important. And this podcast, of course, is recorded. You can publish that in few years' time. And eventually it's going to be the state of the art. This is going to be the mainstream, like those are going to be the mainstream structure. Once we're going to have the ability to integrate it at scale in mass production, gigafactories, from that moment, once we manage to achieve the cost and the scale, there is no reason why not to use it.
Yeah. And how should we think about it in like a climate change context? Does this, what I said at the beginning of the show is that this might enable faster adoption of electric vehicle technology. It might, is it possible that it could make batteries serve new use cases that aren't well served by batteries today? Like I know trucking is not easily electrified. And I don't know, like I'm thinking like even like home energy storage or grid scale energy storage. Are those potential applications as well?
So yeah, correct. As I mentioned, our vision is very ambitious, very big. It's going to be gradually, not in one day, but we want to integrate our structures into any type of battery, any format, any chemistry, and for any application. So you mentioned energy storage, residential energy storage or grid energy storage. Of course, automotive, aviation, marine application, consumer electronic, and so on. So it could be applied into different applications. And the electrification revolution is happening with Addionics and without. So we are not going to be the ones that I will tell you without us, we'll not be able to electrify those. No, it's happening. And with our technology, what we can do is really, as you mentioned, to accelerate and to open and to make it attractive to more variety of application. And if maybe we have like some application that is still debatable if to do it with batteries or not, so we can push it and really accelerate the adoption. What we can do as well is to make some materials which are not very attractive today because maybe they have poor energy or conductivity or power, but maybe with our technology, they can get improved and to be with above a threshold that will be sufficient for some applications. So we can accelerate the adoption of those more environmentally friendly materials, for instance. So this is with a huge impact on climate and environment. And also in terms of, I would say, energy storage, this is definitely can be super attractive. For energy storage, batteries today are probably the best tool vehicle to store energy, better than any other technologies, but they are very expensive. So the cost prevent from grid scale application and other use cases to adapt the battery. And what we can do, we can make it more accessible and to enable to large variety of application to use it. So can push, we can accelerate, we can encourage more and more by, of course, cost reduction, which is going to be happen anyway. What we saw recently that the cost was actually increased 3 times in the last year, which was a bit against all the analysts, I would say, reports. Everyone was thinking that price is going to go down and go down and go down. It's not going to stop. So I believe that prices will normalize again, but still we need to have some technology, structure, physics, AI in the battery field in order to make sure that we are going to get this cost reduction as soon as possible.
So the business model is you would sell these electrodes that would kind of be customized for various applications to kind of balance all the right characteristics of the battery to meet the needs of the application. Where are you? And you have this ambitious goal to be in every battery in the world. Where are you on that commercialization path?
We are working on now with the biggest, I would say, companies in the world, in the automotive space and other spaces, with few companies, really like the best one in the world. With some of them, we are more advanced, some of them more early stages, but the idea is to give them the cell with our structure so they can test it, touch it, feel and see the potential as well. So, and always we're building ourselves, we're building with our components, we're doing that with all the pillars that I mentioned, design, manufacturing, process engineering, integrating that into battery cell, and always building a reference cell that build with the same footprint in the same factory with the same chemistry, which the only change are the physical structure of the electrode. And then you can compare apples to apples and see the improvements. And always we believe that it's better to give the third party to client to test it, because then, no one can tell you maybe you cheated or you did it in your labs or garage. Take it, see it, believe it, and then let's move to more advanced stage.
It sounds amazing. Is there any reason why somebody wouldn't want to integrate this into their batteries?
Definitely. I think we need to understand that the battery industry is very conservative. And today, the main challenge is to meet demand and capacity demand. So most of the companies, they also kind of scared of introducing new processes or new components or new technology, because they need to survive and they need to supply enough cells in order to meet all their contracts, etc. So many companies trying to just survive and to supply what they committed to. So they don't want to be bothered with new technology. So this is a big commercial challenge. And another challenge is technology challenge for us to have enough resources to be able to work with different factories, to be able to customize, integrate that. So the attention, resources, scale up, pain, all of that is associated with that.
So on the technology, you just mentioned one of the technical challenges is, I guess, being able to integrate into all these various different manufacturing environments for your customers' specific batteries. I'm curious to understand the technology a little bit more. So as I understand it, other people have looked at 3D structures, 3D metal structures to replace these electrodes, but where your innovation is in actually manufacturing it and being able to do that at scale and cost effectively. Your website mentions AI-enabled structure optimization. And I was really curious, like, what the heck does that mean? And what is the manufacturing process?
Yeah, so that's a great question. So many people, smart people try to do that. And we are not smarter or we have any secret weapon to be able to solve things that were failed before. But what people did, they used what was available, and not necessarily if it's available, it's suitable. And what was available was very expensive, not necessarily battery graded, and we identified that. So I think that was the root cause of those failures, and the fact that people took what was available. And we invented something new. The manufacturing process is completely invented. It's based on principle of existing processes, but the outcome product is completely new. And that's something which is I think the game changer here in that equation. And you ask what is AI? So as I mentioned, we have like a pillar of design. We can increase surface area, we can have like 3D structure, but how exactly those structure is going to look like? We can have like probably thousands of structures, even more than that. So what we should like build all those thousands of structures and build batteries with those thousands of structures and then test them and then to run it like to 18 months to get like cycle life. It's going to be like forever. So we wanted to develop like battery lab on steroids to understand and to get like fast reaction. And instead of having like 5,000 iteration, how we can reduce it in order to save cost and save time. And that's what the modeling and simulation and all this AI telling us. So we were training the computer to tell us exactly what is the required structure. So our input should be like, we want to get improvement in the energy density. Okay, what should be the structure? And that's I would say, the other layer or pillar in the company, which is very important. And I believe this could be applicable not only to our battery, but in every battery again. And this is something it's missing. We developed that because it doesn't exist.
Cool. So you must have some pretty high level of control over the structure itself. Is it a additive process or a subtractive?
So we are combining both. For the anode side, we're doing like it's additive, and for the cathode side, it's the opposite. But it's not additive in a way that like 3D metal printing or other stuff. So we're doing that like at room temperature from aqueous solution. So it's something that you need to see with your eyes, and that's really cool. And for people with passion, technology, engineering, it's very fascinating to see that.
Can I ask one question about sort of the future of Addionics? And then I have three short questions that I ask everybody, and we can do quick answers to those.
Okay.
What do you think Addionics looks like at steady state? And I don't know if that's 10 years out or 20 years out, or however far that is. What do you think the future of the company is?
So we want to build like a giant, huge company that will be the leader of designing, manufacturing, and providing a 3D, I would say, technology solution for electrodes and for any battery in the world.
Okay, a few last questions just to close us out. I'd love to know what you see in your crystal ball. Are you optimistic or pessimistic about the future of our planet and our species?
Definitely optimistic. I think that's the nature of like entrepreneur. Otherwise, you are fighting against all chances, statistics. So if you're doing that, you must be optimistic or crazy. So I don't think I'm crazy enough, but more optimistic.
Who's one other person or company doing something to address climate change right now that's inspiring you?
In our company or in general?
Mostly, yeah, in general, whether it's in the battery space or other industries.
Yeah, so I don't think like there is one person or one human that is pushing. I think it's a global effort, and also climate. It's not something that one person can do in one location, because one location can keep and push and make sure that no one is going to pollute. And in another country, everything is opposite. At the end, we saw that with COVID, everything is spread. And also like climate change, it's the same. So the effort should be global and this is, I think, also something that can be wrong, that individual trying to take the lead. Things like government should like work together. It's a global effort and it's not individual like task Of course, we need to push, we need to do whatever is needed in order to accelerate that, but it's bigger than just one person.
Absolutely. Do you have any advice for someone who's not working in climate tech today, but wants to do something to help?
Sure. So if you want to be part of that space, I think today is the best time in the history to be part of that. I would call it like industry movement, and there are more openness to hear about ideas, to accept new ideas, to get funding for ideas. So this is exactly the right timing. So just dare and act and ask. Don't afraid to ask and don't afraid to fail. It's also important.
Moshiel, thank you very much for your time and also for dedicating your career to solving some really big problems. I appreciate the opportunity to sit down with you.
Thank you very much, and thanks for the opportunity. And feel free to be in touch as well.
Hardware to Save a Planet is brought to you by Synapse. To find out more about us and how we develop hardware solutions for the world's most ambitious companies, head to synapse.com. And then make sure to search for Hardware to Save a Planet in Apple Podcasts, Spotify, and Google Podcasts, or anywhere you like to listen. Make sure to click subscribe so you don't miss any future episodes. On behalf of the team here at Synapse, thanks for listening.